Hey everyone, so in this video we're going to talk about a little bit of a theoretical topic, and that is interaction between simulation types. I put this into Vellum because Vellum is kind of on the crossroad of this problem in many ways. We will see why. Now, something that is really surprising always for beginners to Houdini is that interactions between simulation types, so like here soft bodies or cloth, then rigid bodies like those boxes, grain and fluids, is actually a massive problem. And I will show you why we can see this here, why this is actually seems to be possible. And spoiler alert, this is because all we see here is Vellum. So when we look at the 5 different main simulation types, pops or grains, Vellum, RBD, flip and pyro, then if you connect them and find all the possible combinations between them where those simulations could interact with each other, it looks like this. And no, we're not a cult. So it's a pure coincidence that this creates a pentagram, but as you can see, it's actually quite a lot of different interactions. You would think it shouldn't be a big deal, right? For example, some grain interacting with rigid bodies or fluids interaction with cloth or something like that can't be that complicated. I mean, Houdini is Houdini, right? Well, surprisingly, actually, this is a big problem because most of those combinations are simply impossible. So all the red ones do not work, surprisingly, which is, again, always a big surprise for beginners. There's one exception, flip and RBD, but even that is really shaky, as we will see. It's not really a stable system. It's always kind of painful trying to do that. Now, you might argue, though, you have seen that in movies or something, and that is true. And there are 2 possible solutions for this problem. The first one is just faking it. So there are all kinds of ways, especially as an experienced FXTD, to make it appear as if there was a simulation interaction between them. And the second way of doing this is very, very often, actually, there is no bidirectional interaction. Very often you have a primary and a secondary simulation. So for example, if something falls into water, then technically it should be stopped by the water. But if it wouldn't, you wouldn't really notice it. What you really notice is that the water reacts to the object that falls in and creates all kinds of splashes. So the primary simulation is what falls into the water, and the secondary simulation is the reaction from the water to that object. So those are actually 2 different simulations simulated one after the other. And very often you cannot tell the difference because you cannot analyze, what's really going on. But nonetheless, this has been a problem for many years. And this is where Vellum becomes very interesting, because with Houdini 19, side effects actually introduced something that they called the Vellum multi-solver, which means you can simulate different things with Vellum. For example, while you can't simulate pyro with Vellum, you can actually use Vellum grains to simulate grains, Vellum rigid to simulate rigid bodies, and Vellum fluids, well, to simulate fluids. And all of them, of course, can interact with each other. There is a problem with this, though, that you have to keep in mind, and that is that the simulation quality of those systems, for example, Vellum rigids and Vellum fluids, will never be as good as the full-blown flip or RBD simulations. But what we've seen before, the simulation that I showed you in the beginning, this is actually completely done with Vellum, and this is why it's actually possible. As a matter of fact, side effects in their presentation of Houdini 19 showed this as a way of showing the capabilities of Vellum. And for a beginner, maybe it wasn't actually that obvious why this is pretty impressive, because as a beginner, you're not aware that before that wasn't possible. And the end result isn't really that spectacular. But for an experienced FXTD, this was impressive because it was simply not possible before. So let's look into this in a more practical way in Houdini. The first thing I want to make clear here is I want to kill a myth that I see all the time online, and that kind of annoys me, and that is the classical multi-solver DOP node. Now, a multi-solver is a node that you can use inside of a DOP network to combine multiple solvers. Here, for example, a pop solver and a rigid body solver. And first of all, this is not actually used to let those 2 solvers interact with each other. So it's not meant to let particles interact with a rigid body simulation. What the multi-solver is doing is it lets those 2 solvers be applied to the same object. So a common case for this would be those rocks which are rigid bodies and we want to drive them with a pop curve force. So what you could do is you create a multi-solver and let the rocks collide with each other via a rigid body solver, and then on top use a pop solver, so you're able to use a pop curve force to drive them along a curve. And this then looks like this. And even though you can't see it here, the rocks are actually colliding with each other. Now, this is complete nonsense because, like I said, first of all, there are no different simulation types interacting with each other. And secondly, the pop curve force is actually usable directly with a rigid body solver. So this is a misuse of the node, because the better approach would be you just use a RBD solver and use a pop curve force directly, and you have the same result. There's absolutely no reason to use a multi-solver here. So I see this all the time and it's complete nonsense. So let's be clear what a multi-solver does and what it doesn't do, and why in practical terms you almost never use it. You almost never need it, because everything that you can do with POPs, for example, you can do with any other simulation type. There are very few cases where you would need that. An example would be if you want some rigid bodies to behave like fluids. So let's imagine you have a big wave of toasters, for example, for a commercial or something. Then it can make sense, because then you can use the fluid solver to make the rigid bodies behave as if they are fluids. But there are better ways of doing this, but this would be an example where you use a multi-solver. It has nothing to do with interaction between different simulation types. So with this out of the way, let's actually look at some real interactions and how they not work. So if you actually look at all the possible combinations, if I'm not completely mistaken, it should be 10 different combinations, as you can see here. Pops with Vellum, RBDs, Flip and Pyro, and then Flip with RBD, Vellum and Pyro, and so on and so on. Now, as we've seen, there's one actual exception that works, and that is Flip and RBD. Everything else you will notice if you try that will not work, which can be frustrating. Of course, I will not show you all of those combinations, but just 3 of them. So the first one is Flip and Vellum. And if you try to do that, and you use a simple merge for this, actually, this is the trick to make this work. You have 2 solvers and you combine them with a merge. And again, it doesn't matter that we actually haven't looked at this yet. The logic is at this point very clear to you. You merge 2 solvers, and then this is a way for them to interact with each other or talk to each other, in theory. In practical terms, one possible result is this. This is the fluid, which is simulated with points, and this is a cloth, which we already know. And then when we run this, you can see, first of all, there's no interaction whatsoever. The 2 ignore each other. Now, what you will see in the only case that worked, which is Flip and RBD, what is the solution here is to change the order in the merge. And now it seems like there's something happening, because it seems like there's some interaction between the fluid and the cloth. Unfortunately, it only appears as such, because first of all, it's super buggy and it's very, very hard to control the behavior, almost impossible, especially for a beginner. And second of all, if we let this run for a little bit, you will see that the cloth is actually not reacting to the fluid. The fluid is reacting to the cloth, but not the other way around. So even if you try that, it's not bidirectional, it's one directional, which is not what you want, because it feels very unnatural this way. And again, there's nothing you can do about this. This is not a matter of some wrong settings or something. It's impossible. Trust me, I tried it for years. It's not possible. Another example is grain and RBDs. So grain, we've seen, basically what we have here is some, grain castle and some rigid bodies, and we simulate them again by merging them together. And if you run this, you will notice again that they don't react to each other in both directions. The rigid bodies do react to the grain, but not the other way around. The grain doesn't realize that there were some boxes hitting it, and in real time it looks like this. Only the boxes reacted to the grain, which of course looks highly unrealistic, and again, there's nothing you can do about it. Side Effects so far was not able to build a system that let those 2 talk to each other in both directions. And the third example is RBD and Vellum. So some cloth and some pieces that fall into the cloth, and as you can see, at first there seems to be some reaction, but if we keep going, then you notice that the boxes are actually not stopped by the cloth. And what happens is this super weird result where the cloth is not able to create any kind of resistance against the boxes, and we get some really weird results. It simply is not meant to work. So what is the solution for all this? Again, there are two solutions. First is think in primary and secondary simulations, which doesn't always work, but many simulations can work that way. For example, what we have here is a cloth simulation and a rigid body simulation, and I simply have just one that drives the other, and the other one will not stop the rigid bodies. So cloth reacts to the pieces, but the pieces are not stopped at all by the cloth. But in a case like that, you don't notice that. And this is what I call the primary and secondary simulation approach. In a case like that, it doesn't matter that it's not bidirectional, because that's not our goal, and the simulation feels correct. Another example is what I explained before. Here I have a rigid body simulation, and we will see something like this in the next chapter, where I have just a tower that falls down on itself and breaks apart. And this tower happens to stay in the middle of the ocean for some reason. So when the pieces, the rocks, fall down, they crash into the water and the water reacts. But even though theoretically the rocks should be stopped by the water, which is not happening here, nobody will see that. So in practical terms, you just fake it by creating this in two steps. And that is, first you simulate the rocks, cache this thing out, and there it is. This is what we just saw. There you go. And this then goes into a flip simulation as a collision object, and then the result looks like this. The fluid just reacts to it like a collision object, like an animated sphere or something. And then we have just the reaction of the fluids, and the pieces just move, and there's no resistance or anything that the fluid can give back to the rocks, because the rocks were simulated in a separate step. And this is actually pretty common, this kind of workflow. And there's one exception, and that is RBDs and flip simulations can actually react to each other. So we can do something like a buoy here. The object is falling into the fluid reacts to the rigid body, and the rigid body actually also gets resistance from the water, which means it can actually float on top of the fluid, as you can see here. Let me quickly create a flipbook for this. So as you can see here, there is actually a bidirectional reaction to each other. Of course, we will talk about this in the flip chapter. There will be a video specifically about this. And as we talked about, with Vellum now, with Houdini 19, and they also call it multi-solver, unfortunately, which makes it confusing, because a multi-solver in DOPS is actually, like we said, something else. But okay, they call it a multi-solver approach. You can actually, in Vellum, create different type of simulation types. So Vellum grain, Vellum cloth, Vellum rigid bodies, and Vellum fluids, and simulate them together in a Vellum solver. A small note on this, by the way, if you want to mix Vellum grain and Vellum fluids, everything else is easy and without a problem. Make sure in the Vellum solver, under advanced, OpenCL, you turn off OpenCL neighbor search. This is actually something that is explained in the documentation, but if you don't do that, it will not work. And with this, we finished the video with the same example that we started it with. Vellum now actually allows you to combine all those different simulations and let them interact. Of course, there's still one big problem, and that is it's all Vellum. So while Vellum is awesome, it's not as good as a dedicated simulation for each of those simulations. There's one specific one for this, and this is the fluid. As you can see, the fluid simulation feels a little bit, CG-ish, and this is because it's a very simplified fluid simulation, not even close to the complexity of a proper flip simulation. But nonetheless, it still solves a massive problem that we had for many years, and to an extent we still have, that you at least now have an option for something like that. Before, it would only be possible with a lot of knowledge by basically building the system yourself or faking it. So again, a bit more of a theoretical video, but I hope it is helpful for you to understand what's possible and what's not. So bidirectional simulations are still a very special topic in Houdini. So I hope this is helpful. Thanks very much and see you later. Cheers.